So we have been talking about finite elements so far. Let's just. I have some ready-made quotes. Let us talk about finite difference from one. Just a second. Let's keep the codes ready. Okay. So we begin with again discretization. So we'll firstly solve for. So basically, right now I'll be just doing some simulations and some optimization algorithms for the next few lectures. So we have the equation dou u by dou t equals dou square u by dou x square plus chi times x into f of t with Neumann boundary conditions ux 0 comma t is 0, which is ux of 1 comma t. So instead of stable heat equation, we'll just consider some instability too, plus k times u. So basically we are solving for ut equals u underscore xx plus k times u plus chi underscore e set e times x into f of t. This is the main equation. Just go on. So we are basically finding the finite difference scheme. Okay. So firstly, in number of discretization steps, I guess we'll just choose small n from someone. Lem of Ron. So after this, we'll just try to do extrapolate things for radiation, conduction, and so on. Because this particular heat equation that we are deriving right now, it doesn't make sense because it has infinite speed of propagation, and I have proved that if you just consider the heat operator, it will have infinite. Matlab, after you will instantly for an infinite length rod, say you're having a point source somewhere, immediately within fraction of seconds you'll sense heat in some other location. So the infinite heat will propagate with infinite speed. So such things doesn't happen in nature, so we have to take some kind of conduction term into consideration, but for now we are just doing this. Okay, nl an. So again we need to find out state space matrices. An is equals to zeros minus 1 comma n minus 1, right? stability margin. So this is the input matrix. We'll just take some output matrix as well. So let me assume, so what will we do? What is the sequence? 1D heat equation, Cartesian, finite difference, 1D heat equation, Cartesian in finite element. Then 1D heat equation, polar, finite difference, and 1D heat equation, polar, finite element. These are the things that we'll do. Okay. So what is del x? Del x is L by n. So we are going to generate the matrices. Okay. Del x is L by n, and what is A11? U1 dot 2u2 minus 2u1 by del x square plus ku1 plus so we'll go with A11 A, and today I guess we'll finish the finite difference scheme. Won't be that hey, plus mu tau del x square, that's it, for I equals 2 to n minus 2, right? And a comma I minus 1, a times I comma I, a times I comma I plus 1 equals, next I'll let us say we are measuring temperature at one end of the rod, 0 comma T. So C Cn of I 2 C of 1 comma 2 equals 1, right? Done. Okay. 1 by del x square by so this is the finite difference. Okay, E underscore n, right? And let me assume that we have something, we have a heating source at, we have heating source in the center of the rod. Let's keep L by 3. So equals to II star del x, and then II plus 1 star del x is less than or equals to 2 star L by 3, right? If and B of II comma 1 equals 1. So we are done with ABC matrices. Just have to write this as global AN BN. That's it, I guess. I guess I'll write. I'll name things systematically as I have to shade. Heat equation 1D Cartesian main code 1D. So I got Cartesian spelling wrong. Cartesian. And now I think I'm wrong. Main code. Okay, you have ABCD matrices, and now you need an ODE system in this. Just copy this code. New function file, and we'll have this. Remove all this stuff, right? AN global AN and BN. Global AN BN. And what is dx dt? Dx dt equals A underscore n star x plus B underscore n. I'll just keep this for now. Okay. I will not cancel. I'll just name this to be heat equation 1D Cartesian underscore ODE underscore code. this. Um, I think OD 8.9 might work in some versions, but it's better that you choose OD 2.3s. This is the better code. I think I'm just plotting things. Yeah. This is x distance. Okay. I have to first fix this to 10 seconds. Zeros. These are the initial conditions. And place this with this. This has to work. Okay. So what is happening? Something fishy here. If L by 3 is less than or equals to L by 10 to 2L by 10. I'm just keeping the. So this is where the heating source acts. This is to go for 200. Length of rod is 1. Why is this happening? I'll do one thing. 9 star L by 10 to 9.5 star L by 10. Something fishy going on. I guess I minus 1, I plus 1. Something wrong with this. Oh, okay. Keep the other boundary conditions. N minus 1 comma n minus 2 minus 1 n minus 2 is this. I'll just cut 10. And this is that. I missed boundary conditions. Just keeping Hmm. Yeah, this is right. So you're having heating source and it's slowly heating things. Okay. Let us change this to 2, right? 2L by 10 to 3L by 10. Just keep 500 steps of discretization. Length. See, to get proper some approximation of PD, you should approximate it by 500 steps or something like that. It will take some time. Don't worry. I'm recording right. Yeah, so this is the profile. 2L by 10 to 3L by 10. So this is the profile that we get. Yeah, yeah. It's appearing to be right. 2L by. Assuming a symmetric source. So we'll test our simulation. Now we are giving a symmetric source, right? So 2L by 3. So we are giving a symmetric source term. So we must get a symmetric thing. That means that then we are right. Hmm. Okay, pretty symmetric. How many steps did I give? I'll go with 200 steps. It's almost symmetric, I guess. It's symmetric 1 by 3. Let me increase the temporary time and number of discretization steps. I mean, let the simulation run. Is it done? Oh, it's still running. So by then we'll just try it on. So I'll be going to optimization next week. So the LQR quadrature, linear quadratic regulator is one of the optimization problems that we have. I think this kind of minimizing a quadratic objective function will be useful in your simulations. Yes, I'm done with the simulation, right? Okay, appears to be thing. With more accurate solvers, we'll have this thing anyway. So let me do one thing. I'll just percentile this. Sorry. Yeah. I think we can keep all of this in one space. Okay, I'll just try something for 5 minutes. Okay. Okay, I'll do one thing. I'll start with finite element simulation tomorrow. Let me check what will happen if we increase the stability margin. Okay. Length of the rod is 1. Stability margin is 10. Okay. So 10 is not good enough. Okay. Okay, I can do one thing. For n is equals to 10 is to 10 is to 100 and that is printing n. Okay. I'm just trying an quadratic optimization problem. Just a second. I'll explain about optimization problem theoretically and so on uh, by next week. I think I can do something. I can remove all this mu's and I can just add an equals a underscore n plus mu star ey. So combine this one, right? Okay. L underscore n. Okay, I'll teach the optimization problem next week. Today we have simulated the finite difference method. I'll try to do some quadratic optimization on this with underlining dynamics with the parabolic heat equation, and then I'll just continue.